Okay, I'm going to talk about TempleOS threads. In TempleOS, there's no distinction between process, thread, or task. Everybody uses the same address map. Sometimes I say it's multi-threaded but single process. That's because disk requests are not broken in pieces. So if you do a long operation, everybody else has to wait for the disk. So single process but multi-threads is probably the best way to describe it. So TempleOS is unusual because it doesn't change the map, so the address map. So if I say while true yield, what this does is swap out the current task and schedule the next task. So if I do this, it can do it 4 million times a second. Nobody else can come anywhere near that fast. That's because it's single address map. So when it changes tasks, it saves a context and restores a context. The scheduler basically does 3 things. It saves the registers when you save the context. Saves the it does some bookkeeping for how much time the task is used. It saves the floating point stack, or floating point registers context. And if there's any breakpoints, each task can have its own breakpoints, and you want to remove those when you swap out a task. So that's why it can do it 4 million times a second. If you think about it, I have a 3 gigahertz processor, and if I take 1, 2, 3, let's just take that divided by 4. I think we're taking 750 cycles. 4 million. Well, anyway, so all it has to do is save 16 registers. The floating point is I think 512 bytes, and there's a if you have a lock, then that uses a lot of time. A lock is used for multicore multitasking. It has to do a couple other things when it saves and restores. It checks. It has to schedule. It's a round-robin scheduler, but there's a wake-up jiffy on each task that tells when it should be rescheduled, and it has to check if it's ready to be rescheduled when it goes around in the robin. It also checks there's a flag if it's waiting for a message. So when you it doesn't spin when you're waiting for a message. It checks it and skips it if it's waiting for a message. Anyway, so let's look at a 1-core multi-threaded application. Now it turns out that if you look at the tasks there's a Seth task for each core, and then on core 0, this is not very good. Hold on a second. Each core has a Seth task, and then on core 0 you have a window manager, and anyway, the window manager redraws the screen 30 times a second. So when you do a game application, we're going to look at Zing. Let's look at, this is a game. You can shoot arrows. So the when the game starts, it calls preempt. This turns preemption off. Basically, what I did for all of these little subroutines, I made the default argument the most popular, and the most popular thing you want to do is turn preemption off. Now, TempleOS is the only operating system that lets you turn preemption off. What that means is no, it will not schedule another. It will not interrupt you in the middle and schedule another task. So some people assume that it locks everything out. No, this is cooperative multitasking, and when we call get message, we voluntarily yield the core, and it schedules the next task. So first of all, the draw it is a callback that the window manager calls, and that draws the arrows. You can look right here. Here's where it draws the arrows. Anyway, so when we start up an application, we supply a draw it callback, and we have some infrastructure to first of all, the draw it call gets called 30 times a second, and it can be preempted. So this gets tricky. So you don't want to change queue links in the middle of a draw it. We put the arrows in a queue, don't we? So what we do is this preempt. It's a circular doubly linked queue. Hold on a second. Let me show you what I'm talking about. When we when we fire an arrow, we allocate a little chunk, then we put it into a doubly linked queue, and then when we draw it, we go through the next pointers and draw all the arrows. You might ask what would happen if we were interrupted and it hit a bad pointer for the queue. Well, the reason we can get away with this is because we called this preempt off. The preempt off means we're not going to be interrupted in the middle of changing the two pointers. The only time we get interrupted is when we voluntarily yield at the get message. So there's another task, the animate task, and this is what changes the XY of the arrow. It changes the XY of the arrows right here, and the default is to have preempt off when you make a new task. When you spawn a new task, the default is preempt off. So we can turn preemption on, but obviously preempt off protects you during the startup until you turn preemption on. But for this animate task, we want to leave preemption off. And so what that means is there's mutual exclusion. So what that means is we're never going to be interrupted between X and Y. And we go ahead and this window manager sync damn bird. This says wait until the next time the window manager is scheduled. So the window manager might be irregular. So we when we update the arrow distance, we want to see how much time has elapsed. And so I could just as easily have done sleep, I don't know, let's say 25 milliseconds, but that's not quite as professional. Well, anyway, we only need to redraw. We only need to change it every time there's a redraw. So now the animate task is we have some infrastructure. There's a routine called settings push and a settings pop. And what this does is when you do settings pop, it goes ahead and it kills your animate task. And it restores preemption to what, remember we changed preemption. So as a matter of fact, when you're at the command line and you say include zing, when we exit, this is the same task. So if we turn preemption off, we would leave the task with preemption off, but the settings pop takes care of turning preemption back on. So anyway, so let's look at another example, Bugbird. Okay, so that it's a little game. Now this doesn't turn preemption off. It takes a different way to do it. We have a flag called game reset, and when we start up, we what we call a song task. We create a song task that just plays the song over and over. Preemption's off. That's okay. So and we call an animate task. And the animate task, this is kind of weird. Anyway, it checks if the reset flag's been set, then it reinitializes the game. Otherwise, it updates the bird X, Y. The bird only has a Y, so there's really no danger. But in a normal game, you wouldn't want to update just X and not Y and get preempted. It wouldn't matter that much. But so I don't think we have any Q links. Q links are a big concern. Anyway, so this has a flag, and if you restart the game, what it does is it sets the flag, and that tells the animate task to reinitialize the game. So this is just another alternative. Now, so far we've been talking about single core. When we get into multicore, it gets a little trickier, but if we look at the eagle dive, what this does is when it initializes it, I think it's I'll have to check. Okay, we have an animate task. All that does is update the position of the airplane, or bird, whatever it is. Looks like init is putting one task on each core. When we do init, we create a draw. These are to assist in drawing the screen. So we go through. MP count is the number of cores, and we that's kind of funny. We pass the MP count into it, but then we use. I think that's a bug. I think the intent was to pass that as a parameter. Oh well, I'll fix that later. Anyway, so we go through, and the spawn has a argument that tells the first argument is the address of the code that you want to run. Second argument is a data item that you're free to choose, and what we're doing is telling fs is the parent task. We're basically telling it which task is the boss, and then we have a name, and then this is the core. So you explicitly put a task on each core, and let's go look for AP Eagle Dive. And anyway, so there's the animate task. Like I said, all it does is updates the well, I guess it does a couple things. It updates the bird location, and it checks to see if you've eaten a fish. Believe it or not, you can eat fish in this game. That's the point. So the bootstrap processor is core 0, and what this does is this is the master, and what it does is it tells the slave tasks to draw the screen. We draw on a memory image, and then the update copies the image onto the screen. And this is in charge of telling the multi-core tasks to start and stop, or to start, where I think it calls this over and over. So I guess in the game loop, we're checking for a key, and then we're redrawing the screen. And I don't know why we're not pausing. I guess the pause is in the maybe this. Where are we pausing? We have to. We can't just go continuously. Okay, there's the window manager sync. So we're synchronizing with the screen being redrawn, and we're writing to a device context the image of the screen, and then all the draw it does, which is the callback. All the draw it does is blot the image. So we're living a little bit dangerously when it comes to multi-threading. The draw it has no. Well, anyway, we're updating this live, and we have no synchronization. We're doing it. Well, it's synchronized. The window manager sync basically is kind of like protecting one end. Anyway, I'm getting distracted. Okay, so we want to talk about the. It created a boot an AP. This is, I think it stands for auxiliary processor. BP is BSP is bootstrap processor. AP is the BSP is the master. AP is the slaves, and the slaves draw the screen. BSP is the master. Anyway, all I was going to say is we have bits to keep them in sync. When the application is finished, we want to this is critical. Okay, I'm going to take the time to explain this. Okay, so when we start up, it calls init. Init spawns some processes, and it spawns a process on each core. When we shut down, we have to when we do the final shutdown, where is that? I'm going to look for MP. We have app done. Okay, let's see. App not done, app done. So we have a flag for when the application is done, and the slave processes on the other cores wait until the app is done, and as long as it's not done, they draw the screen, and then once it's done, they all have to check out, and we cannot exit the program until all the applications are done, and we have to wait until each of them clears its bit, and as long as app not done, we have to sleep. MP end is called at the end of the where is it? Maybe it's in cleanup. There it is. Okay, when we do cleanup, we call MP end, and that the reason you don't just exit this application is because you would yank the code out from underneath the other the task on the other cores. You don't want to yank the code out from underneath, so you have to do an orderly shutdown, and actually you have to wait until each core has finished, and you don't exit the task until you exit all the slaves. Anyway, otherwise it would crash because you would yank the code out from underneath. I just want to see if okay, I accidentally changed that. Anyway, that's all I wanted to show you. I made a change to the code. I have to fix that.